stare. Non so se ti sento, fai più vicino, così poi ci alterniamo.
So, good afternoon to everybody. It is a pleasure. It is a pleasure today to have here Akamas, Stefano Doni, and Mara Oriani. They will present the company, and they will also give you some tech insight about optimizing the performance of cloud services. As you know, later on today, we have the possibility of individual interviews with them. They are already scheduled, but if there is some late arrival, someone who wants to join on the flight, just let us know at the end of this lecture. And then there will be the aperitif in city center in the Akamas branch here in Padua. So thank you so much for coming, and please.
Thank you too. So, hi everyone. My name is Mara, and as Professor Ferro told you before, I work as HR business partner within Moviri. So today, I would like to give you a very quick overview about Moviri. And then I will leave the stage to Stefano, who is my colleague and who is now covering the role of Chief Technology Officer at Akamas. So, what is Moviri? Moviri is a consulting, IT consulting and software house. We have core area of expertise that are performance engineering, analytics, cybersecurity, and IoT. So we are a group of around 200 people, and we work globally. So here in the next chart, I would like to show you like our timeline, because I think it's a bit twisted. So I think that I'll try to be as much clear as possible. So two professors in 2000 founded Moviri. So the very first product we developed was Neptune, and it was working and operating within the capacity planning and optimization field. Then Neptune was acquired by one of the biggest American multinational IT multinational company called BMC Software. And after this operation, Moviri started investing in some other new software houses. And so in 2007, we launched the business of ContentWise, which is a recommender system, so like a Netflix model. Then in 2014, we did a great investment in Q5, which is a tool operating in the anti-fraud field. And so together with Q5, we work a lot within the financial service industry. Then we invested in Arduino, which is pretty famous. I think that most of you already know Arduino. And then last but not least, in 2017, we started launching Akamas. So basically, together with me, there is Stefano, who is one of the most senior and tenured employee at Akamas. He's the founder of Akamas. So he will go through Akamas later. So just to let you know our global footprint, as I already mentioned to you, we have around 200 people all over the world. We have our HQ, our head office in Milan. But over the years, we launched the Padua hub. So in around 2 years ago, we launched the office here in the city center. And now we are 10 people here in the city. And then we have 2 American branches, one in Boston and one in LA. and like a commercial presence in Southeast Asia, in Singapore. As you can see from the chart, we operate globally, so we operate in more than 30 countries, and 40% of our revenue comes from international deals. So we work literally globally. Okay, so now I think Stefano, it's your turn. I will leave the stage, and then we will have the opportunity to talk later.
Thanks, Mark, for the introduction. Hi, everybody. I'm Stefano Doni, co-founder of Akamas. So this session is going to be to introduce the problem that we are solving. So basically, Akamas is a new software company born in Italy, which is doing some pretty cutting-edge stuff, which is kind of similar to what Google, Facebook, Twitter, the most advanced engineering teams are doing in Silicon Valley. So we are doing that in Milan, actually, and also here in Padua. I want to make this interactive, so I will ask questions, so feel free to answer any, no stupid question, really. So let's make this interactive. We have a couple of time today. So the problem, so what is the problem? So let's, as everybody know, seen a picture like that before. So what's that? Microservices, does anybody know what is a microservice? Yes?
So basically, despite the traditional monolithic applications, which were you put it on one set of stack and it run once or as a single package, microservices give us the flexibility to develop multiple different services or applications that can work together
yeah. That's great. That's great. What's your name?
Ali.
Ali. Oh, that's a great answer. So basically, I know that you are starting to develop web application in this course. When you will move to the kind of enterprise world, start to work on bigger system, most likely you will kind of see a picture like that. So probably not that complex, because that is actually the architecture of Twitter. It was published more or less 10 years ago. Today, probably it's kind of different, but what you see in this picture is basically each piece that is very small here is actually one microservice. So basically, you are coding a web application in Java today, running, I don't know, in a Docker container, something similar, right? So that's just one microservice, like Adim actually suggested. So there may be modern companies like thousands, tens of thousands, if not hundreds of thousands of microservices. Each of them basically may run with different application stacks. So you are developing with Java, some may run with Golang or with Python and other languages. Most likely they will run on cloud native systems like Docker and Kubernetes. Everybody knows Kubernetes, ever heard of it? No? Right? Container Dockers? Right. Okay, when you develop your Docker container, basically when you have to run it in production across perhaps thousands of nodes, you won't actually use Docker. So you will use a platform like Kubernetes, which is basically a cloud native management platform that was open sourced by Google in 2014. And today is becoming the standard. So everybody right there, even in Italy, but also in Silicon Valley, pretty much everybody is using Kubernetes. So by the way, studying it, that's something that may improve your CV actually. So all those microservices may be written in different languages, running on cloud native platform. And the question is, from a performance point of view and reliability, how do you make this system, which is a very complex system, fast? So companies are searching for ways of giving this kind of complex architecture. By the way, here you can see different kind of communication flows between each other. So perhaps you will have some very hot microservices. For example, this one is kind of a router. So every tweet that you send basically is being processed by this single microservice. So it's just one microservice, but maybe huge from a scale point of view. It may have thousands of instances. But then, as you can see, basically forwards requests to other microservices. So for example, you may have one microservice that does authentication, the other that actually checks the spelling, etc., or process the analytics, so the fact that you do likes, etc. So that's the idea. And the thing is that companies are looking for ways to make systems that are complex like that, to make them more reliable, cheaper, and actually faster. So that's the task of pretty much performance engineers, like we have said in the beginning. So that's what you end up doing for actually in your daily life, but also taking care of reliability. So of course, that's a very complex interaction. So if you send a tweet, or I don't know, if you do a payment with your bank account, most likely you will end up communicating with, for example, 100 of microservices. So the chances that each one is down at the given moment is not that small, because you need to be able that all our 100 microservices need to be up and available to respond to your request in a given response time. So that is very important. At the same time, you want that to cost as less as possible, because if you create the system on the cloud, all of a sudden you are going to discover that this is very, very costly. So at the end of the month, you get a very huge bill on AWS, Google Cloud, or Azure. So next priority becomes, how do we make this system still make it run faster, reliable, but cost less? So that's a challenge, basically. A very common challenge also today is in kind of economic, in a way, downturn, how to make system become actually cheaper is one of the biggest challenges for IT systems, IT teams. Any idea about how to make this system cheaper or faster? What do you do? What would you do if you were the software engineer working on, I would say, a couple of those microservices? That's a good point. You had the recent post, yeah, from us. Yeah, that's one point. So they went back. A team of Akamas of Amazon actually went back to monolith. Not whole Amazon. Yes, because they say microservice may be expensive. Reality, probably there was a mistake in the design of the original system, but that might be an option. Not very popular, but might be an option. Other ideas?
That balance your cost and reliability.
So you scale it,
yeah.
Right?
One star and another one, and it's maybe like operational research, having the average between something not so expensive, but that works. We work at every moment.
Yeah, that's a good answer. Actually, kind of similar to what we were talking about. What's your name? Giovanni, good answer. Any other approaches? So if you are developing one of these, you are writing the Java code, what you can do?
Generally, for example, you can have better load balancing, so that even if you don't scale horizontally, and you have
Great question, good answer.
that way, you can at least have each service. You have each less load for each service process, or different situations.
Yeah. So auto scaling, so kind of similar to, so being able to actually, one of the problems of the cloud is to actually follow the traffic pattern. So if you have peaks, you will have many instances. So this microservice basically kind of duplicates, you add more instances. So the code is the same, but each system will take care of additional part of the load. And when the load actually decreases, you will actually remove instances. So it's called elasticity in the cloud. So it's one of the biggest benefits of the cloud, because basically you pay only what is needed for the traffic that you have to manage. So those are good answers. Other two things that you can do is that, of course, if you are working on the code, you can tune the code. And if you ever write some program and it was slow at the beginning, right? Very, very, very common. So there are tools like profilers that lets you actually understand where code is spending most of the time and how to make the code faster. So perhaps you can change the algorithm, so you can write different code. The other choice that you have is you buy better hardware. So on the cloud, you have different hardware options. So the processor, basically, you buy an Intel, you buy an AMD processor, you use ARM processor. So there are actually 300 kind of different options on the hardware. So you can also choose that. So that's the idea. So that's the topic of the talk. But if you, there's actually a third way, that is what we are going to focus on today, which is about configuration. So let's actually zoom into a kind of a single microservice. So if you think the Java code that you write here, you write it into the top kind of layer. So it's your application code is running here. But if you think your application code, it will run most likely in a framework, right? So how do you write code today? Do you use any kind of framework in Java? Spring, that's great. By the way, it's the most common one. Even Akamas is written in Spring. So Spring, it's a framework that actually avoids that you develop lots of, I don't know, database connection and state management, transaction, observability, logging, all of that, you don't have to touch it. So that you are sitting on top of a Spring framework. Then you have the application runtime, very, very important. What is the runtime that you run your Java microservice on? JDK, the Java virtual machine. We are talking quite a bit about the Java virtual machine. So the Java virtual machine sits there, right there. But the JVM runs most likely, as we have said, within a container. So that's a kind of another layer. And where does the container run? So in the cloud, you don't have servers anymore, right? Or you still have them. Where does your container run? Actually, there may be another layer here. So where does your Docker container run? Where are you running it today? Sorry?
Top of a server.
Yeah, exactly. So on top of a server, so you most likely have the operating system of the server. Anyway, if it's a VM, it's a virtual machine, you will also have the hypervisor. So that's kind of another layer, actually. And then you also have the hardware. So the hardware may have different architecture. So you may change from AMD to Intel, very different CPU architecture. So it's the same code you can run on very different CPU architecture, and there are many of them. Here on the left, you can see the kind of different configuration options that you can see, that you can actually choose. So that's the power that you have in your hand. So on the JVM, you can see you have literally 700 parameters. So that's mind-boggling, but it is what you have today. So the JVM that you run in your laptop is basically the result of 20 plus years of engineering by Oracle. So best minds in the industry have optimized those runtimes, and basically now it's open source. So it's great that you can run those without paying huge amount of licenses. Years ago, it was that was the norm. So you couldn't run actual enterprise software in your laptop. Now you could do that. So you can study all those parameters, and all those parameters, as you are going to see, can impact the performance. So basically, the fact that your application sits on top of those layers means that at the end of the day, what cares about the performance or the reliability of the cost is basically the application. So you care that your microservice is fast, your microservice costs few bucks, or at least it's cheap to run, and it's reliable. So the fact that depending on how you choose those parameters, you will get different performance and scalability attributes of your architecture. You will get different resource usage. When I say resource usage, I mean, do you have an example about, have you ever looked about your container, how many resources are using? CPU and memory. Yeah, that's what I mean. Docker, do you use Docker? No, what do you use?
I use Docker once.
Okay, and when you develop your Spring Boot microservice, what do you use?
To ship here, and like a very easy backend, work very fast because you have to get compost.
Right, that's. But if you use Docker, you do Docker stacks, you can see CPU and memory usage of your container. So CPU and memory usage of your container that you can see also on your laptop translate directly to the cost on the cloud. So depending on how big is the container, how much CPU and how much memory do you use, that is the bill that AWS gets to send to you at the end of the month. So that's kind of simple, actually. So the question is, how do you make your system consume less CPU and less memory? That's the question. And all those options have great impact on that. Also availability and reliability, because if you do you know any specific parameter? Have you ever touched any parameter here on the JVM when you run your services? Java heap, do you know what is it? Never touched. Anyone? I don't know. How many gig do you give to your microservice, the memory? Never try to change that value. All right, it's something that you can configure. We are going to see a few examples. So how much basically CPU memory is consuming your container? Do you allocate for the container? And then how much memory do you grab for the JVM? Those are all configuration options. And you need to be able to understand those because you will be asked to actually size them properly. So after you have done the work of writing the code, next question is, okay, how many CPU do you need? How much RAM do you need to run that? And that's a question that you need to be able to answer. To let you understand actually the complexity. So let's dive a little bit into the JVM. So the JVM is, I'm glad that you are using this technology because that's by far the most common technology in the enterprise today. Here and in the Silicon Valley, basically everywhere. The JVM is, the Java ecosystem is so common. Basically Java language, you may have Kotlin, other languages, or there are other languages that may run on the JVM, but the key thing is that the JVM is the runtime, it's the engine. And the JVM basically, that's, by the way, a great book. If you are interested in what I'm saying, I suggest you to read this book. Java Performance is one of the Bible. And you can read here what, basically that's by an Oracle guy. Oracle is developing the JVM, and reading what he says. So the JVM has hundreds of command line options. These wishes can provide performance engineers a gold mine on possibility to explore to the pursuit of the optimal configuration for a given workload and a given platform. So how can you actually understand what are these options? It's a very simple command line. So I will give you the slides, but it's very simple. With this option, by the way, here I'm running basically a Java container. Java minus this option, print flags final. Basically, it's printing all the flags. If you count the lines, you get this number. So you can do it in your laptop, very easy, just a command line. So there are literally 674 command line options. And you may have some fun in understanding what they mean. So it's not always that easy because some of them are not even documented by Oracle itself. Some other are pretty known. But to give you an idea of what they do. So let me dive a little bit deeper. So I guess you didn't touch this kind of topic in this class, right? So the JVM architecture, any idea about that? First time that you've seen or you have seen something like that? No. All right. Other training? No. If you zoom into the JVM, so you will find a very complex engine. So it's a kind of engine with 700 screws that you can turn. Like when you bring your car to the service, they can tune, for example, the computer runs to actually, I don't know, make your system run faster or use less fuel, for example. So that's very the same thing. What is very important is that one of the key properties of Java is that you don't have to manage memory as an application developer. I guess that's very known for you by you, right? So have you ever developed in other languages like C, something like that, right? What do you have to do with C when you have to allocate a bunch of memory? What do you do? Sorry? Yeah. So you have to explicitly manage memory. So you have malloc to allocate memory and free to free the memory. So it's very hard for developers to actually be correct. So write programs while managing memory. It's very easy to make the system crash completely. Benefit of the JVM is that complexity is not, in a way, something that you need to manage anymore. So the JVM does that for you. So that when you do a new object in the JVM, where does the JVM store this object? Into the heap here. So that's one big region into the heap. And then when the heap fills up, what does happen? Anybody has any clue? There's a process that is called garbage collector. So basically, it basically scans periodically the heap and tries to freeze up memory. So this is something that is happening. The other thing is that Java is Java a compiler language? Is that Java an interpreted language, or what is Java? Sorry? Compiled? Who says compiled? That's a joke that we also have in our team. Surprisingly, we get different answers also in our team. So who says that it's a compiled language? Right? Who says it's an interpreted language? Nobody? All right. So the reality is that when your source code gets translated to something that is called bytecode. Bytecode? Yeah. Who runs the bytecode? There's a piece in the JVM that is called the interpreter. So bytecode is a kind of higher level. The VM, the virtual machine, is because this bytecode speaks about, it's not x86 instructions. It's a kind of higher level language that works on any processor. But the beauty of Java is that without you doing anything, Java has a just-in-time compiler. So it observes the program as it is running in production. And basically it optimizes and compiles the code on the fly. So that's great. So very few other languages does that. And with this kind of trick, the JVM can run programs that are sometimes faster than C and C++. Why is that? Because this guy here is heavily optimized by Intel engineers, by AMD engineers, and they can use the deep instruction of the CPU to make your code run faster. Like you write code in Java, so that's great. So you don't have to write in C or in assembly or lower level languages. Also, the compiler has options to tune. Any garbage collection algorithm to choose. How much memory do you give here to the JVM? It's my original question. You can choose that. I assign 1 gig here, 2 gig, 10 gig. So pretty much any kind of piece here is basically configurable. So it's a very complex problem. Of course, you cannot do anything. For Java, the JVM has default values, but look here at what happens using default values. So here we can see just one microservice. We can see 2 metrics here. One is the response time. So you can see seconds. So this microservice basically is responding in kind of 200 milliseconds, a little bit less. And that's the CPU usage of this service. So we have 2 pieces in this chart. Let's look at this leftmost part first. So here you can see CPU usage. CPU changes because actually we have different kind of load patterns, kind of daily peaks, and you have droughts, etc. So you can see here the amount of CPU that we are using in millicores. Basically, 1,000 millicores is one core, one CPU core. You can see here, basically, we are using 1.5 cores. So 1.5 CPUs. So 1.5 CPUs may translate to, I don't know, $100 per month on the cloud. Then we change the one configuration. We didn't change the code, we didn't change the infrastructure. The load is always the same, and look what happens. CPU usage gets reduced by 60%. That basically translates to 60% lower cost on the cloud. Would you like to spend more on the cloud, or would you like to spend less on the cloud? That's the question. What did we change? So in this case, it was just one of those 700 parameters. We changed the garbage collector. So the JDK that was mentioned before comes with 5 different garbage collectors. Each of them is treated for different purposes. G1GC is the default garbage collector since Java 9, kind of old one. It still is the default one. So if you run JDK 11, JDK 17, whatever, you get this one. This is a very good GC, but sometimes it uses quite a bit of CPU to do its work, because also the garbage collector is using resources. So this CPU is not only used by your code, it's used also by this guy. If this guy is not that efficient, what happens? So look at when we change it to parallel GC. That's another GC that was the default before Java 9. In Java 9, Oracle decided to change the default values, and now we have this one. Why Oracle changed it? Because parallel is well suited for kind of batch programs. One of the things is that when garbage collection runs, your application is completely stopped. That's key. So it has to free up the objects, and it cannot do that while your application threads are changing the objects. So your application threads are completely stopped. So then run the garbage collector, and then your application starts running again. So then one critical piece is that how much time does the garbage collection take? Because if it takes too much, your latency, your performance will be impacted. So if the GC takes 100 milliseconds, all of a sudden you will get 300 milliseconds for the response time. So because parallel in some situation has a high response time, they change it to G1, which is a clever design that actually tries to clean up the objects while your application is running. It's called concurrent GC. So just to give you a hint about what are the options available and how they can change really dramatically what is happening under the hood. Make sense? That's an interesting analogy that I like to make, which is about Jackie Stewart. I don't think anyone has ever known this guy. It was an old pilot, F1 pilot, but he was 3 times world champion in the 60s, so last century, kind of old guy. Those guy was actually able to win many races, but I think his secret was he didn't have the fastest car. So how Jackie Stewart was able to actually lap the other players, sometimes by seconds. So by the way, those are very early machines, so it was also very dangerous to push that kind of limit. So Jackie Stewart was able to actually complete the races much faster than the others. And his trick is what he called mechanical sympathy. So Jackie Stewart didn't have the fastest car, but Jackie Stewart knew the car the best. So he spent countless hours with the technician, with the technician that were actually adjusting the engines, adjusting the tires. So he spent literally hours and hours trying to know better the car that it has available. Then the other players, drivers actually made much more practice on the actual circuit. So his approach was, let me understand better the car so that I can push to the limits. So that's the idea. And he's invented this term, which is very important, very like what we are saying, which is mechanical sympathy. So in mechanical sympathy, basically means knowing your hardware. If you know your car, you will be able to extract higher performance. And basically in the IT terms means that if you are able to make software and hardware run in a kind of harmony, we can achieve much better efficiency. For example, we can use much less CPU, as we have seen before. Sometimes all the layers in the stack that we have seen before, you just run them with default values. They are kind of fighting each other. So there's no harmony, but actually quite the opposite. So that's one reason why you can get much higher performance without spending more money on the cloud. So that's the interesting idea. So how can you do that? So of course you can change the code, you can buy better hardware, but most importantly, what we are focusing on, especially with Akamas, is how do we do tuning? So how do we select this configuration, the best configuration to get those kind of benefits? Here, by the way, you can see some ideas of kind of tunable. So we have seen the runtime, the JVM memory, garbage collectors. On the container, you have to select basically how big is the container. On the hardware side, you can select the instance type. If you go to the AWS, basically service list, you will find hundreds of different instances. But also at the application level, you may have some choices. The Spring Boot framework provides several choices. For example, how do you connect to the database, the connection pool, etc. All configurable, hundreds of options. And MySQL database, 500 parameters. That's the idea. Everybody is pretty much running with default values, but you have these kind of benefits so that you can achieve. So the question is, how can I actually exploit this kind of possibility? It's kind of hard because if you kind of do all the combination, you will get basically billions of possibilities because of course all those parameters can basically influence each other. So it's a very complex problem. That's a problem that we are addressing with Akamas. So today, pretty much anybody is working on this problem. So we have just a few competitors spread around the world. So kind of like Silicon Valley, US, pretty much Israel. So we have a few companies that are tackling this kind of problem, which is a huge problem because everybody in the industry is affected by this problem. How the industry is trying to cope with this problem. So let me show you basically the process. So everybody is doing this kind of process. So it's a kind of very simple process that we also ourselves have been doing for close to 20 years. and that is a process. So basically, there are tools, like I mentioned, that lets you understand all those metrics that I assumed before with great detail. So there are tools that monitoring tools, in a way. So you can buy products. If you go working in a company, most likely you will be able to use that products already available. So your instrument is like in a way being able to see all the response times, if you use it, etc. So that's the first step. You need to have observability. So you need to have visibility of the performance of the system. Then comes the next step. So you need to understand what you are going to tune. That is hard because you have all those options. So most likely today, that's a trial and error process. So you analyze the usage and you say, okay, there may be a problem with the garbage collector. Let's try a bigger heap. Let's try changing this other GC. Or perhaps my Spring Boot, I can change that option because I read a blog that mentioned, I don't know, connection pool. But those are hundreds. Then somewhere you come up with one parameter to change, and then you change one parameter. Notice you change just one. Because what happens if you change 3 parameters or 2 parameters?
But you don't know which change make that block better, and perhaps if you remove the other 2, it can be even better.
Exactly. So the problem is that you quickly cannot understand anymore. If you got better performance, that is great, but what was the cause? It was just one of the 3 parameters, or perhaps it was a combination of the 3. Maybe that's what happened. So that's the idea. So typically, performance engineers, everybody in the world is doing this kind of thing. And then, of course, you test the system with a new configuration. That might take, I don't know, 1 week. Then you push your new configuration in production, and then basically you wait. You will gather those charts that we've seen before, and then you basically repeat. That's how the industry is solving this kind of problem. Is this a good process in your view? Not that much. So it's slow, it's manual, it's slow, it's kind of error prone. It requires deep skills. Most of the times, you need to be an expert for the JVM. You need to study JVM. There are experts like 20 years just focusing on the JVM, and they don't understand how to tune it. So it's not an easy thing to master. And then actually it doesn't scale because it's manual. You need to do that. Think about doing this for 1,000 services. We engage with customer tuning one microservice for one leading customer that we have. So it's not a kind of, in a way, beginner. They took tuning one microservice, they took 2 months of skilled engineers, just one of them. We need a better approach. So that's what we do at Akamas, basically. So another analogy is that we are still kind of in the last century from that point of view. So on the cloud is really very advanced, but you have all those kind of nodes and switches. So like flying an airplane in the last century. The idea of Akamas is that let's build a smarter system. Kind of like a Google Maps, a navigator, that you can state to the system, okay, that's my goal. I want to run with less cost. I want to run with faster performance, with higher reliability. Just do it. You are much better suited than my brain to actually tackle this kind of complexity. So that's the idea of Akamas. So we have built a product actually working on this idea a couple of years ago, and I wanted just to summarize the idea of this product, and then I'm going to show you some examples of what we have achieved actually applying artificial intelligence, because that's the secret sauce, right? So how do we make performance engineers' brain move it into a program basically that is able to tune and understand how to tune all those parameters without human being involved, so without the effort, without being error prone, while improving the safety, etc. So the idea is that we build this product, which is actually a startup based in Milan. We are, as we are seeing with Mara, basically, it's a spin-off of Politecnico of Milan, the mother company. Now we are basically running within the same company. So the idea is that we had this kind of experience working in these domains, is kind of 20 years doing performance engineering ourselves. But also thanks to our relationship with the university, we have very skilled people working in AI and machine learning. So basically the idea is that let's combine the two approaches. So we have expertise in the technology stack. We know that very well, but we do that manually today. Then but we may use artificial intelligence to automate this kind of tuning. So that's the idea of the product. To build a smarter system so that engineers doesn't have to have a better life, basically, doesn't have to do this kind of work manually. So the idea of the problem is that it's full stack. So remember the stack that we have seen before. So Akamas can tune every layer of the stack. So it's not just tuning, I don't know, the JVM, it's just the JVM. That's important because, of course, customers have different technologies. So you need to be able to tune them, every technology, basically. But also it's important to tune all the layers at the same time. Because as we have seen, if I change a garbage collector, perhaps I need to adjust the container size, or I need to change, I don't know, a parameter on the Spring Boot. So everything is affected. So if I just change one layer and then I come and change the other layer, there's no guarantee that the two changes actually are not fighting against each other. So you need to be able to tune all the layers at the same time. How do you do that? Of course, you need some kind of smart AI to do that. So we invested quite many years in doing research, and that's also something that we have done also in collaboration with basically you as a thesis project. I will talk about that later. And we have patented AI algorithms, both here, Europe and also US, because actually we didn't find any ready available approach. So it's not that you use, I don't know, deep learning to tune this kind of systems, because actually there are many constraints to apply traditional AI algorithms to this in a kind of problem. So one problem is that why, for example, we don't use neural network is that you need to be very quick to understand how to tune the system. So neural network may require millions of samples to be tuned, for example. We cannot afford those kind of trial and error, because actually also customers want a recommendation and works kind of immediately. So that's the idea. And also they need to be safe. I will talk about that later. Goal oriented, so that is very powerful. Like the navigator example that we are talking about before. So you as software engineer still wanna say what is the objective. So you have performance problems, you have reliability problems, you have cost problems. So what do you want to achieve? Do you want to achieve lower cost, or do you want to achieve faster performance or higher reliability? So it's like for Google Maps, for example, you can, sometimes ago you could actually choose, you want to have the fastest route or the cheapest route. Now it gives you different options. So for example, sometimes it recommends, the default metric to optimize is the time. So it gives you the fastest route, but perhaps it's the longest one. Sometimes Google starts recommending you that there are other routes that are shorter, for example, if you are running out of battery or fuel. So that's the idea. So you get to select the goal. So that is made possible by AI. So with AI, you can actually say, okay, that's a goal. AI start to change those parameters and look for ways to improve your metric. So that is important. Automated, because as we said, we cannot do that kind of work manually because it's simply too big. Working at this scale with this kind of thing manually. And the last thing, which is very important, needs to be safe. So that's one of the biggest challenges in AI. How do we make AI recommendation and prediction safe? You see that also with, I don't know, ChatGPTs, things like that. Here we have kind of the same topic. So when Akamas recommend a change, how can I make sure that I apply this change and it is not slowing down my system, for example? So that's important. So that's a major area where we have invested, created patents to make sure that AI doesn't recommend actually bad configurations. And that's something that is also related to the thesis opportunity that we have. Make sense? Any questions so far? Right. So let's talk a little bit about the kind of machine learning techniques that are available in this field. By the way, have you attended classes related to machine learning? Right. Okay. So here you can see three kinds of major approaches. One approach that actually we worked on in the past quite a bit is doing models. Pure network models. Have you ever seen models like that? Yes, some of you. So basically, it's like designing the airplane, working on the wireframe, like in the CAD system. So basically, it's completely you don't have the aircraft, but just working on a very simplified model. So it's very simplified, but still allows you to study some aerodynamical properties, kind of high-level properties, similar to what we do with systems. So we have used this approach in our past products. Actually, it doesn't work that well for tuning because actually those models are not accurate enough to predict if I change a garbage collector or the JVM, what will happen? That's not going to work. Another approach, which is kind of towards more kind of realistic stuff, is simulation based. So the analogy with the aircraft is that you actually build an aircraft. It's a smaller aircraft. Why smaller? Because it costs less. You can iterate quickly, but kind of you can study more realistic airflow properties, etc. Similarly to what we can do, we use this approach with performance. Basically, we do stress tests, we do benchmarking. So we take this one application, we do a load test, meaning that we stress the application and we measure the response time, the throughput, the CPU usage, memory usage, etc. And we repeat that for each single configuration, potentially millions of configurations. In fact, this kind of process takes literally months, but at the end of the day, it takes a lot of time. So you have to kind of be clever to simplify the problem because otherwise it's too big. But at the end of the day, you get a data set that is very powerful and you can use to study the system. So instead of optimizing the real system, you will optimize the benchmark. So somewhat more realistic, and it's sometimes very useful. So that's an idea. The third approach is actually, in a way, the best one, because you actually have the real aircraft. So you have built the aircraft, you put a test pilot in here, and then basically it tries to push the aircraft to the limits. Of course, the problem here is that it's very expensive because you have to build the aircraft. If the aircraft is not good, you have to spend a lot of millions to actually build another version, with changes, etc. But that is actually the utmost, in a way, realistic system. And we do that actually when we actually need to optimize the real system. So sometimes the only way is that you put a system in a test lab or even in a production lab, and you start changing the configuration to see how it behaves. So there are different ways. Also machine learning approaches like reinforcement learning that is able to actually interact with the system. So change one parameter and then measure how good is the new configuration in terms of performance, reliability, etc. So that's the idea. Make sense?
What are trees?
Yeah, pattern trees is a way to explore basically the parameter space that we have seen before. Is not really a flat parameter space. So let me give you this example. If on the JVM you can select G1 garbage collector, you can select parallel garbage collector, and there are others. If you select parallel, you will have access to kind of different parameters that are related to how parallel works. So those parameters doesn't make sense if you use G1, for example. So in theory, this parameter space is structured like a tree. So that's a way where you can exploit this kind of structure when actually finding the best configurations. So that's one approach that we tried at the beginning. So maybe in a way faster to identify anyway the best configuration if you are able to exploit this kind of relationship. Okay. Welcome. So let me show you some example about what Akamas achieves. So what we achieved in real life applying this scenario. So here you can see a chart, an actual screenshot of our product, where you can see what we achieved. So the objective here, let's say that we have a Java microservice like the one that you are developing. It's slow. You don't know why, but you want to make it run faster. So the objective that you give to AI is, okay, response time. You can literally say minimize response time. So Akamas will tune the JVM parameters like garbage collector, heap, etc. So you can see all those dots is the results, the response time of the application while Akamas is changing the configuration. Cross dot is 0%. What does that mean? Is the baseline configuration. So basically, what you have today might be the default settings. So let's say that you have that point is 0, so it's a relative score. And then Akamas start changing the configuration. As you can see, the first one that being tried actually make the application as lower. This one might be, I don't know, 30% lower, 50% lower. But then Akamas understand that it needs to go to the other direction and start actually make the application pretty faster. So in a very few experiments, actually, for the experiment, so for configuration that was tried, it was already 30% faster. And then you can see how Akamas CI explores. So it basically visiting the space and then tries to understand where is the most promising region in the configuration space, and actually is able to make the system run faster and faster. So at the end of the day, in a matter of 24 experiments, it may be 1 hour, sorry, 1 day or 1 weekend of automated tuning. So you won't be here sitting at this tool, but actually just you define the goal and then you let it run. He was able to achieve this kind of benefits. Interesting or not? Right? What is interesting is what was the configuration that Akamas found in this example. So the baseline was actually what everybody does, just assign the heap size. So I want to give 1 gig of RAM to my Java application. Everybody is doing pretty much this kind of high-level settings. We gave Akamas 6 parameters, more kind of in-depth. We also have the maximum size, so the same parameter here. We allow Akamas to tune that. We also allow Akamas to tune, for example, new size, because within the heap you have different regions. New is where the new objects, when you allocate them, will end up in the new region, for example. But we also we like to change the garbage collection type. Remember the G1 versus parallel. Again, in this case, also in this case, parallel was the best one to make the application run faster, etc. So you can see Akamas what is the best configuration, then you can take this configuration, basically apply to your system in production and start having these benefits. That's another interesting example. Databases. MongoDB, do you use MongoDB? Right? Any idea about configurations for databases? What do you have to configure at minimum?
First thing that comes to mind is like the data. So, for example, for GPS coordinates, where we say each second at least 1 reference, we want to make sure that we don't overuse the size.
Right. Good. By the way, which database do you use in the Postgres? 400 parameter or 300 Postgres.
We don't do the configuration.
You don't do the configuration. One of the typical parameter is how much memory do you assign to the database? That's a key parameter. Here you can see basically in this 3D chart is basically a surface plot that shows you how the performance of the database. The z-axis is the throughput, queries per second. So you have a database, you do a stress test. Basically, you inject how many queries per second you can. So you have a program that basically stresses the system with thousands of queries per second. And then you measure how many of them the database can reach. In this case, we tune just to 2 parameters. So we tune many more, but it's interesting to understand how this kind of curve actually is shaped in the real life. So we do a 2D plot, 3D plot. So we change the MongoDB cache size, which is how much memory do you assign, and then we change the Linux storage redirect. So you probably don't know this parameter. So this parameter is related to mechanical sympathy. So the performance of the storage in the operating system is typically dominated by the time that you basically ask the disk to read a sector in a way. So the time that you ask one question is very long. When the disk is able to read this amount of data, basically you can select how much data you can read. So let's say that I'm interested in a block of the database because I'm doing an index-based query. So I need just one block in the disk. But as it takes quite a bit of time for the disk to locate this block, while I'm reading this block, it makes a lot of sense to read more data, so that I will bring in more data into the operating system cache. And if the database needs those data, the additional data, perhaps you are doing a scan in a table. So most likely you will need the additional rows, right? Doesn't make sense to just ask one single row, because it takes a lot of time to ask one row. So there's a parameter in the Linux OS that says how many additional rows, how many additional blocks. While I'm here, how many additional blocks I may ask. The default value for this parameter is 0. Actually, it's 0 is our representation. It's like 128 kilobytes in the Linux OS. Why 128 kilobytes? I don't know. Somebody decided it was a good default value, and you will get to have this kind of values. So the default configuration that for MongoDB was read at 0, which means 128 kilobytes. The cache is 15 gig. Notice that this is a 30 gig database instance. If you install the MongoDB on a, I don't know, 30 gig instance, by default, MongoDB takes half the RAM for the database. Why is that? There's a reason for that, because the other part is left for the operating system. Because when you read data from the disk, it gets cached into the operating system memory. So the idea of the default value is that let's put at the half of the memory, because if you are reading a lot of data into the disk, chances are that you will need this kind of cache memory. So you will improve the performance. But that is dependent on what you do with the database. That's not always the same. So let's look at this surface. So again, two parameters that we basically the throughput. You can also see the color here. 100 means basically the baseline configuration. So the color here that you can see, when you see 100 is basically the performance of the original system. What is very interesting is that if I keep a Linux storage reader at 0, I can even assign all the memory to MongoDB to the database. The performance doesn't dramatically improve. That's interesting. So if I don't change this parameter, I may even spend twice on the cloud. I get marginal performance improvement. So your boss, you are going to ask you why we are not getting more improvement. We are spending double the bill. That's interesting. Other interesting way to read this chart is that without using more memory, if I increase the redirect, I can basically get 150% more performance. That is very interesting, because if I'm not touching the memory and not spending more on the cloud. We let Akamas explore the surface and look at what it found. He found a configuration, a region, the yellow one, which is 200, which actually pretty much double the request per second. Again, with the same kind of cost on the cloud. It identified that for this particular workload, it was best to increase the relay. Again, let's say that you are doing scans on the table. 8 might be, I don't know, read 1 meg. As I'm going to read 1 block, read many of them, and let's bring them on the memory. So the database queries will be much faster. So that's the idea. And you can see that actually the highest performance was also using all the cache. Again, there's something that if you read the MongoDB database documentation, they say, okay, those are the parameters, you can change them. You need to test for your own workload. So there are no silver bullets. So it's not that this configuration is the best. Let's use that, depending on your application. So that's the idea. Make sense? The other, and that's actually the last example that I have, is remember the stack, the cloud, the hardware piece. The stack at the bottom was about the 300 option that you have on the cloud. So that is very interesting. So we asked Akamas to identify the configuration that provide the most cost efficient on the cloud. Cost efficient means highest performance and lowest cost. So basically, it's a ratio between queries per second that we have seen before divided by the cloud cost. So the best configuration that Akamas improved 40%, 41, very great. But you can see, by the way, in the baseline configuration, the price on AWS was $67, and the throughput was kind of 2,700 queries per second. So that was the baseline. Then we let Akamas explore. Akamas found a configuration much better that actually provided 36,000 queries per second. So very much increasing the throughput. But it was also costing much more, kind of 10x. If you do the ratio, because the goal was to increase the ratio, it's still very positive. But there may be an option that is too costly for me. But look at what Akamas found in the fourth configuration was very interesting. Found a configuration that actually somewhat managed to increase the throughput 12%, and at the same time it reduced the cost by 24%. So 67 to 51. So the ratio turned out to be 32%, but that way actually Akamas was able to give me a better, kind of cheaper instance on the cloud. And by the way, you can see here the difference. So the baseline was using an Intel processor with 15 gig of RAM. That was the disk, 70 gig GP2. That's R4 large is the way that you can the instances are named on the cloud. I just found another instance which is called M5A. M stands for memory optimized. The A is important because it's using an AMD processor. AMD is actually providing much cheaper CPUs. By the way, you can use that also on your laptop and your PCs at home. But still manage to see half the memory. So the database was having higher performance with half the memory. How good is that? So imagine being able to run your car with kind of double your miles per gallon without spending more. So that's the idea. So that's the end of the talk. I want to just conclude with kind of wrapping up what we do here at Akamas. I think you have seen those kind of what we like to do is not working on small problems. We like to work on big problems. So that problem is basically affecting everybody in the industry, even the Silicon Valley companies. And in fact, we are talking with many high-profile companies right there because basically we have kind of a unique approach to solve this problem. Especially if you like working machine learning or performance engineering, we advance the state of the art. We have done patents. We also published actually papers, our research team in top-notch conferences last year. For example, we published a paper in a very large database conference, which is kind of the top conference in databases. So our paper was accepted. It's a very hard to be accepted. So other players like Microsoft and Oracle are striving to get accepted to these kind of conferences. You get to know with a great team because actually we work with a lot with these kind of problems since for a living. So you have a way to jumpstart your career, and also we have lots of interesting, in a way, free fruits on the Fridays. We have beers also on the Friday. We are trying to bring it back after the COVID, etc. So that's the idea. And what we like to do also with the universities work with thesis. So when you do thesis and internship with us, you get to work on those problems. So you don't get to work with, I don't know, consultancy projects because we need manpower. We need to advance. We need ways to find better AI to solve those kind of problems. So our theses are actually always research thesis, and that gets published, etc. So that's the idea. So last slide is about the contacts. So I guess you already know us, but if you want to reach out for HR or thesis opportunities, that is it. Thank you very much.
Questions, guys? Don't be shy. Okay. You can ask about the technology, you can ask about the challenges, you can ask about how it's working and being in a company. What are the requirements? Are there expectations?
Giovanni?
Yes.
Giovanni.
So the basic idea is to use AI and a very deep understanding of the machine to optimize, and the workflow that a company asks for a optimizing process, and even in AI and knowing and hoping they use Java, of course, and the idea is to find the best method for them to save money and be better. The global idea of Akamas.
Right, great question. So basically, we are a software company. So basically, we build the product. So the idea is that it's not that we can do. Sometimes companies ask us to actually help them solve a particular problem. You can use Akamas, you can use your brain, whatever. So that's especially what we do in the consulting space. But our focus at Akamas is to build the product. So basically, we sell the product, and then the customer use the product basically constantly to optimize their application. So that's what we prefer, because we like to solve the problems for the world in a way. So it's not us that needs to be able to use the product, but it's built for also from the user interface needs to be easy to use. That's another challenge that we have. And also, if you remember, the stack is not just about the JVM. So basically, we seek to solve all the configuration problems. So if you have databases, if you have, I don't know, Python, Golang, it's very common on Kubernetes. It has its own set of parameters, so it's not Java specific. So the problem is, how do we configure our stack? Basically, that's the idea.
So for the Akamas project, right? So you have many parts, you have automated deployment or distant other things. And I want to ask, do you implement each step yourself, or for example, you use, for example, Jenkins or other applications for different problems?
Yeah. That's a good question, because the customers typically have their own DevOps tools. Like you mentioned Jenkins, you may use, I don't know, Bitbucket, you may use security scanner, you may use Kubernetes, others, GitLab, etc. So customers today are actually already implementing those kind of products and processes in the development lifecycle. Even inside Akamas, when we build the product, we have pipelines. So everything is kind of industrialized, because it's a process with code reviews, etc. So customers typically already have done this, because actually it's all what you need to do to write great software. And as we have said, every company is becoming a software company. They most likely have already done that. So what we need to do here is integrate with their environment. So it's not that we come and we ask, okay, let's throw everything away. We put our stuff. Doesn't work, because everybody wanna, we minimize the investment, because they don't have that much time also to work on optimization. They want to have solutions that actually are easy to use, integrate, and then you can start optimizing. So we built a lot of the product that is not related to machine learning, is integrating with those environments, connecting with the environments. Question? No?
I have a more general question. What is the kind of career or development path an engineer can have in different kinds of companies? Because you are saying that we want to change the technology, we build the product, we are not seeking for consultancy in the power. So what's the different kind of works that you can find out here?
Sure, makes sense. Mauro, you want to start? It's an interesting question.
So generally speaking, let's call it the entry level is a junior software engineer role that can be like a back-end engineer, or can be a front-end engineer, or can be both front-end and back-end, so a full-stack engineer. And then you can grow in the role and become like a software engineer without junior. And then, of course, senior software engineer, engineering manager. And so my point of view in terms of career development, basically, it is divided into, from one side, there are subject matter experts, so people who are really technical, so people who be technical, continue developing the code, and people who taking on a more people-oriented role. So, for example, means team leading. So means managing people. That means motivating people in your team, which is, quite different. You need to be empathetic. You need to be really people-oriented. You need to listen to people of your team. And so this is, a bit different. And here we are talking about roles within the companies, because if I go back at the very first slides, okay, no. So the first thing I said before was that Moviri is also a multinational IT consulting company. That means that we work for clients. That means that we are also consultants. So being a consultant means that you can work for different clients at the same moment. So that means that you can work for, Vodafone 1 week, and then the week after you can work for a major bank, for example. So you need to be very flexible. You need to, change topic very quickly. So you need to be, very flexible, dynamic. And so it's a bit different. I don't know if you already have something in mind, if you already know what kind of career would you like to take in your next future. Think that here, this is a master's degree, right? Yeah, so you're approaching the working life. So for people, for students who are interested, then I'll stay here together with Stefano, so we can have like a one-on-one interview, and let's do all the the interviews you would like to do.
Are you working with Java only, or any other? Are you working, you mean? I do teach Java, all the things I'm working with Java. So basically, Akamas can, we build the product to be flexible. So to basically we optimize any stack, any language. Maybe Golang or I don't know. Ruby and .NET, also Microsoft languages are very common. So basically, pretty much you have to consider that today is the most common languages. So Java, .NET, Golang, all of them are running with this approach of a runtime, because all of them are dynamic languages, meaning that they manage memory for you. So pretty much all of them have this kind of problems, with benefits and problems. So when you have automatic memory management, you have garbage collection. So you have garbage collection also in Golang, in .NET. You will have containers. You need to size the containers irrespective of what runs within the container. So it's pretty generic. The product itself is developed in Java and Python.
Not maybe to the project, but what's the position of Akamas stuff working?
Working. Yeah, that's a good, smart question. Yeah, so we are currently working hybrid. So we don't have strict rules on the smart working policy. We generally suggest to our employees to come to the office at least 50% of their time. Why 50% of their time? Because we think that it is really important to have your time at home when you are, really focused on what you're doing, so you don't have distractions, you don't have people around you talking out loud. But at the same time, we strongly believe in the power of the office, because in the office you can, sit next to your colleague and exchange opinions, exchange information, so share some knowledge. So we are, we are trying to push on a hybrid way, and 50% of the time at home and 50 from the office for us it's ideal for now.
May I ask you what's your view on that? Are you?
So, I don't know, maybe I'm tempted because on one side, not working fully remote, of course, tempting because you don't have to waste time traffic or either. On the other side, I cannot imagine working without being touch with people. So I'm asking for people that struggling with the idea. When you were talking about career, I can imagine myself on 20 years or on 10 years still just programming because I need to touch with people. And on one side, waking up, having a coffee, and sitting on your desk is amazing. On the other side, see that all my colleagues are just an icon on the screen. So I don't know, I'm still deciding.
That's a key point because what I really suggest is to start actually working in the office, especially at the beginning, because otherwise, how can you learn? Experience that people that you have in the office, because that's one of the greatest way to learn. You just, I don't know, do the stand-ups, participate in the course. Of course, you are listening, but you get to miss quite a lot of conversations. So, especially at the beginning. Our suggestion is always to actually, if you can, unless you are very far in the office, you have problems, of course, you have this flexibility, but try to be even more in the office because it's sometimes people seek fully remote work because it looks fantastic. I can work on my own, etc., but you are really missing lots of growth opportunities.
I think it's like being at the university. It's the same. Of course, being at home, it might be, comfortable. But of course, you miss lots of opportunity of not being here and connected with other students.
Now the consultancy versus software engineering kind of role who is for consultancy, just to, if you are thinking about doing consultancy work or development work, any idea about that? Consultancy? Just you, okay. Yeah. Development, software engineering. Right. Good choice.
And what about the others?
And what about the others? Marketing or HR, perhaps, why not?
Was before the higher of software engineering.
The others, any idea?
Is someone interested in analytics, cybersecurity, IoT, analytics? Cybersecurity, okay, nice.
Okay, guys, any other questions? So, next step. So, we have an individual interviews. I have sent you an email this morning with the schedule that I divided by 5 and 4. The room is on the 4th floor, on the other side, so where the professor of you can send the transfer that you are here for the children, they will let you have. Okay. Any questions on this? I think the rest. Yes, you can send your CV, continue by a later. It will turn out either current 5 because we have 5 people in the slot at 4, and so that's the other 5 people in the slot at 5. Okay.
also for the next year?
Yeah.
Okay. Okay. So join us last night, this night also, if you wanna eat something.
Yeah, of course. We will wait for you in our office in Via Sant'Andrea in Cuba. So in center, so we will arrange the video. So everyone of you will be invited.
And even if they look either in the form or outside. That's very I will send you address to all of you. Okay. So, okay. So, please. And